Chapter 8.3.2, the particle zoo. By the end of this section, you should be able to define leptons and quarks in the standard model. Describe the symmetry of the standard model describe that the symmetry of the standard model predicted the existence of top quark. Explain that every particle has an antiparticle. See, every particle has an antiparticle. Deduce the properties of particles and their antiparticles. So we will see. This table is important. Now this is the table that is about the quarks. We have 6 types of flavors of quark. Some books will use the word flavors, some books will use the word types. Okay, or here you can see family of quarks. We have 6 types of quarks or 6 flavors of quarks: up quark, down quark, strange quark, charm quark, bottom quark, and top quark. It's easy to remember them. Up, down, see, bottom, top, strange, charm. Then these are the symbols that we use for these quarks, and these are the charges. I will tell you an easy way to remember this. First we will go through this part. The family of quarks, these are subject to the strong nuclear force. Now we have strong nuclear force and weak nuclear force. Weak nuclear force is also called the weak interaction. So the strong nuclear force acts on quarks. Like I said, we will see the details. I have also indicated this in the notes. So over here you can see this is the note of the lesson. Strong nuclear force acts on quarks, acts over very short distances, explains alpha decay, holds the nucleus together. So the strong nuclear force holds the nucleus together, because in the nucleus you have protons and neutrons. Protons repel each other. So if they repel each other, how can the nucleus stay together? The nucleus stays together because of the strong nuclear force. And remember, this strong nuclear force acts very short distances in the range 10 to the power minus 14 meters. Then opposite, we have strong nuclear force. Then also we have weak nuclear force. Weak nuclear force is also called weak interaction. This weak nuclear force acts on both quarks and leptons and is responsible for beta decay. Strong nuclear force explains alpha decay. Weak nuclear force is responsible for beta decay. Now again we will see some examples of alpha decay and beta decay. It's there in the next subchapter. And also we have the classification of the particles. So you can see the details there. We'll first go back to what we were doing. Okay, so we have this table of quarks, and also we have the table of leptons. See, family of leptons. These do not feel the strong nuclear force. See, again, if you go over here, strong nuclear force acts on quarks but doesn't act on leptons. However, the weak nuclear force, also called weak interaction, acts on both quarks and leptons. This is important. Okay, so we will see the fundamental particles now. We will see the details of these quarks and leptons, how they are classified and all that. After a century, so standard model is here. After a century in which scientists rapidly discovered many subatomic particles, they have now established a theory for how these come together to build up the things we see around us. This theory is known as the standard model, as the idea of the atom as indivisible was swept aside by Rutherford and Thomson. Remember, J.J. Thomson, Ernest Rutherford. In the O-level class also you would have seen this when you learnt about the atom. So remember the names we saw in the previous lessons. Also we went through this. When we went through alpha particle scattering experiment, we heard about Ernest Rutherford. We heard about James Chadwick. Geiger and Marsden. And then afterwards we learned about the discovery of the neutron. Then we saw the name James Chadwick. The J.J. Thomson also we saw when we learned about the history of the structure of the atom. The J.J. Thomson plum pudding model. You would have heard this even in the O-level class. Okay. As the idea of the atom as indivisible was swept aside by Rutherford and Thomson, so the idea of proton and neutron as fundamental has also been overturned. In the past, people thought that protons, neutrons, those are the fundamental particles. But now we know that even it can be broken down. Proton is made up of quarks. Neutron is also made up of quarks. we have probed inside these two nucleons, those are the protons and the neutrons, and discovered that each is constructed from smaller particles known as quarks. The electron has so far survived as being considered fundamental, so we couldn't further divide the electron. However, it has two partners, similar types of particles, and each has a neutrino associated with it, forming a group of 6 fundamental particles known as leptons. So here we have the table of leptons. Now remember, here we talked about the electron, and then with the electron we come to these fundamental particles. The leptons are all classified here. Electron is in the family of leptons. So however, see, the electron has so far survived as being considered fundamental. However, it has two partners, similar types of particles, and each has a neutrino associated with it, forming a group of 6 fundamental particles known as leptons. So these are all fundamental particles. Now remember, this is the first one, this is the second one, and this is the third one. So that's why they say 3 here. However, it has 2 partners, including itself it will be then 3. So electron, electron neutrino, that is 1, muon, muon neutrino, 2, tau and tau neutrino. Again, I have also given this table in my notes as well. You can see over here, see, electron, this one. So you have the neutrinos, then also we have the so muon, muon neutrino, tau, tau neutrino. So you can see muon, then the neutrino, and also tau. So altogether you are getting the 6 fundamental particles. So so it's basically electron, muon and tau. Electron, muon and tau. Then you have electron neutrino, muon neutrino and tau neutrino. So like I said, we can consider this as 1, this as 2, and this as the third one. That is the 3 that they are talking about here, 2 partners and the electron, altogether 3. So each one has a neutrino attached to it. That's why in total you have 6. So remember, electron, electron neutrino, muon, muon neutrino, tau, tau neutrino. Same thing is there in this table also. Okay, you can see the particle. These are all fundamental particles. Leptons are all fundamental particles. Then the symbol, the antiparticle, is also given. These 3 columns are important. First 3 columns in this table are important. Okay, so scientists like to see the universe as balanced or symmetrical, and we have now found that quarks are also a group of 6, although only the lightest 2 are found in protons and neutrons. So scientists like to say asymmetrical, and we have now found that quarks are also a group of 6. So you can see the 6 flavors of quarks here. 6, although only the lightest 2 are found in protons and neutrons. Now again, remember, what is this? Mass. And you can see this mass and this mass are the smallest out of these masses, all these masses. So again, let me go back to my notes here. I can show you what the, okay, so this is the proton and this is the neutron. Proton is made up of 2 up quarks and 1 down quark. You see UD. Neutron is made up of 1 up quark and 2 down quarks. So you can see both the proton and the neutron are made up of only up quarks and down quarks. Now if you go back here, you can see up quarks and down quarks have the smallest masses compared to the other quarks. That's why this sentence here says, over here you can see, although only the lightest 2, that is the lightest 2 quarks or flavors of quarks or types of quarks, are found in protons and neutrons. The heavier quarks are found in rarer particles. The 2 groups are distinct because quarks can undergo interactions via the strong nuclear force. Okay, so again, if I go back to my notes here, you can see the strong nuclear force acts on quarks but doesn't act on leptons. Weak nuclear force acts on both quarks and leptons. Okay, whereas leptons do not feel the strong force or strong nuclear force. It is the strong nuclear force that binds nucleons together in the nucleus. Now what are nucleons? Protons and neutrons, which are in the nucleus. Again, in the note I have mentioned this. See, holds the nucleus together. See, strong nuclear force. It is the strong nuclear force that binds nucleons together in the nucleus. In each group of 6, there are 3 pairs with a similar order of magnitude for mass. And these are known as the 3 generations of matter, figure A. The masses of particles in the standard model increase over generations. So these tables are important. The family of leptons, these do not feel the strong nuclear force. So you should remember these names, okay? First and second columns are name and symbol, and also the antiparticle. I have given that in the notes here already. See, also the quark table is here. This also is important. Then leptons and the antiparticles. Okay, let's go through this part. Generation, name, symbol, charge, mass. I will tell you an easy way to remember this. Okay. Also here you can see the name, the symbol. It's again, I think in a way it's easy. Now, by the way, this is a Greek letter. I have uploaded the Greek letter also in the notes. You can see the different Greek letters here. And tau is a Greek letter. And mu or mu, you can see me. Some people pronounce this letter as me also. Me, mu, mu. Okay, but in physics we pronounce this as mu, right? This Greek letter. Okay, then you can see the subscript. See, tau is there for this. So we use this Greek letter which looks like a V for the neutrino. Okay, then also you can see charge. That is again easy because electron, we can say that is the elementary charge, like -1. Then muon also -1. Tau also has charge -1. Go back here a bit. Yeah, it's not given here, right? Okay, so then the others are 0 0 0, easy to remember. So remember whatever that doesn't have that neutrino part, you can remember it as having a charge -1. Easy to remember. See, electron, muon, tau, they have charge -1 -1 -1. Then once that word neutrino is attached, what do you have? Electron neutrino, muon neutrino, tau neutrino. Their charge is 0 0 0. Easy to remember. So you can remember it like this. Electron has a charge -1. Then the other one is what? Muon and tau. They also have charge -1. And once that word neutrino is attached, then the charge is 0. Okay. So symbols are important because these symbols are even used in the equation, the nuclear decay equation. You will see in beta minus decay, beta plus decay. If it's antiparticle, we use a bar on top, like what I have here in the notes. We use a bar on top like this, see, to indicate that it is the antiparticle. But remember, we use this when it is the neutrino, either electron neutrino, muon neutrino, or tau neutrino, if that is the antiparticle of that. Okay, so we use this. Anyway, if it's a neutrino, we use this Greek letter nu. Yes, so you can see these are the Greek letters. This is the Greek alphabet, and see the letter is nu. It looks like a V, but it's actually a Greek letter nu. Okay, then I will tell you an easy way to remember this also. The name, symbol and charge. Symbol is easy. See, up, U for up, so U, D for down, so D, S for strange, C for charm, B for bottom, T for top. Easy way to remember. Okay, so this also I think now you can understand. If it's a neutrino, electron neutrino, muon neutrino, tau neutrino, we have the Greek letter which looks like a V, that is called nu. Nu, the Greek letter nu, Nu. It looks like an English letter V. And I told you how to remember the charge also. Now similarly, I will tell you an easy way to remember this. See, up, top, charm. Those are affirmative words, right? Those are words that mean something positive. Now, up means something positive, right? Charm, charming, you can remember, instead of charm, you can remember charming. Charming is something, a positive word. Top is also something like positive, a positive word, right? So here you can see the charge is positive. positive, positive. So up quark has charge positive 2/3, charm quark has positive 2/3, and top quark also have positive 2/3. All of them have the same charge, and here the charge is 2/3, so it's the majority charge. So majority also means something positive, right? 2/3, you can think 2 out of 3, the bigger portion. Then we have the other quark, which is the down quark, strange quark, and bottom quark. So down, again, it's something, some kind of like a, we can think of it like a negative word. Down, bottom, strange, you know, it's something representing something negative, right? Down, strange, bottom. So then you have the negative sign, see, minus 1/3, minus 1/3, minus 1/3. And the remaining amount of 2/3 is 1/3. So the what is left over is going to the down, the charm, and the bottom quarks. You can think of it like that. So 2/3, the remaining amount is 1/3, but remember you have a negative sign here. This way you can remember it easily. Okay, so up, top, charm, they have charge plus 2/3, plus 2/3, plus 2/3. Then down, strange, bottom has the charges minus 1/3. The family of quarks, these are subject to the strong nuclear force. These are also important. You should know this. They are subject to the strong nuclear force. Then you can see the masses of particles in the standard model increase over generations. So this is what we saw. See, top quark, bottom quark, and the masses are given here also in giga electron volts divided by c squared. I showed you how to do the conversion. Then you can see top quark, charm quark, up quark. Now see, you are using the same color here. They are using the same color, top, charm, quark, meaning something like positive, right? So you can think of it. Then down, strange, bottom, blue color. Okay, then we also have what? The leptons. The leptons are shown in gray or silver here. We have the electron, muon, and tau. Okay, leptons. Then we have the electron neutrino, muon neutrino, and the tau neutrino. Now when you go up, what happens? The mass increases when you go up. So here also you can see the mass. When it's a neutrino, the neutrinos have a very small mass. I think you have learned it in the O-level class also. When you learned about beta minus decay, beta plus decay, you would have slightly heard it, that the neutrinos have a much smaller mass compared to the mass of an electron. So here you can see the electron has a higher mass than the neutrinos. See here, this, and even this one, right? So 0 less than 20, 0.51. Okay, so you can see here from this table, I think it's easier to see electron neutrino, tau neutrino, muon neutrino. Okay, then let's see the next part, the last page here. And also there are definitions. These definitions are important. Standard model is the name given to the theory of all the fundamental particles and how they interact. This is the theory that currently has the strongest experimental evidence. Quarks are 6 fundamental particles. Okay, I wanted to mention that. I think I mentioned briefly. So the fundamental particles are the quarks and the leptons. Okay, so quarks are fundamental particles. Leptons are also fundamental particles. So in total you have 12 fundamental particles, 6 quarks and 12 leptons. Okay, so quarks are 6 fundamental particles that interact with each other using the strong nuclear force as well as other forces. Okay, so remember I had explained that here in the notes. Strong nuclear force, yeah. Okay, so strong nuclear force acts on quarks. Again, showing the same thing because it's important. Okay, quarks are 6 fundamental particles that interact with each other using the strong nuclear force as well as other forces. Now, for example, between two protons, you can have the electrostatic force of repulsion. But here we're talking about quarks. Anyway, leptons are the 6 fundamental particles which do not interact with the strong nuclear force. Only the other 3 fundamental forces. So we have the weak nuclear force, also called the weak interaction, acting on both the quarks and the leptons. And also, because these have charge, there is a electrostatic force of attraction or repulsion between these particles which have charge. The strong nuclear force is an extremely short range force between hadrons such as protons and neutrons. Now, what are hadrons? Hadrons are made up of 2 or 3 quarks. Okay, so before we go to that, I want to just show you this part here. The strong nuclear force is an extremely short range force. See, strong nuclear force acts over very short distances. Okay, I have put that in the note here. Then also you can see force between hadrons. Now, what are hadrons? Hadrons are made up of see, I have classified here. See, hadrons are further classified to baryons or mesons. Now, if it's a hadron containing 3 quarks, it's a baryon. If it's a hadron containing a quark and an antiquark, then it's a meson. So hadrons are made up of either 3 quarks or 2 quarks. Here 2 quarks. 2 quarks means a quark and the antiquark. Right? Then so these are hadrons. Hadrons are made up of only quarks, either a quark and its antiquark or just only quarks. So what is the force between quarks? It's the strong nuclear force. So strong nuclear force acts on quarks. So that's why this is mentioned. The strong nuclear force is an extremely short range force between hadrons such as protons and neutrons. Examples of hadrons are protons and neutrons. Why? Because protons and neutrons are baryons. Baryons are made up of 3 quarks. Again, in the note here I have shown you the proton and the neutron. You can see they are made up of 3 quarks. If they are made up of 3 quarks, they are classified under baryons, and baryons are classified under hadrons. Okay, and also you can remember quarks and leptons are fundamental particles. We will, I think, yeah, we can add that to this note here. Okay, so first we'll go through this part. Okay, so that part is now clear. For each particle there exists an antiparticle. So for every particle we have an antiparticle. This was mentioned, I think, previously also. In the beginning we saw that for every particle there is an antiparticle. Okay, let's quickly try to trace it somewhere here. I remember. Okay, so it's there somewhere here. You can see properties of particles and their antiparticles. So if particle and there means, that means it should have an antiparticle. But here also it's mentioned. For each particle there exists an antiparticle which has the same mass, but all the other properties are opposite to those of the normal matter particle. So everything is opposite except the mass. Now, for example, charge is opposite. If it's the antiparticle of that particle, then it will have the opposite charge, but it will have the same mass. So again, for each particle there exists an antiparticle which has the same mass, but all their other properties are opposite to those of the normal matter particle. Okay, so remember, but all their other properties are opposite to those of the normal matter particle. All right, so these definitions are important. Now we will go back to what we were doing here. Okay, we finished this first page. Now let's go through this bit. Only the first 3 quarks, up, down and strange, were known from the middle part of the 20th century, and the charm quark was discovered in 1974. The symmetry of the standard model indicated to scientists that there were other particles that had never been observed, which should exist, the bottom and the top quark. Experiments were carried out to find these, and the accelerated experiments at Fermilab discovered bottom, that is bottom quark, in 1977 and top quark in 1995. Current particle theory holds that all matter in the universe is constructed from combinations of some of these 12 particles. Now what are the 12 particles? The 6 leptons and the 6 quarks. So quarks and leptons are fundamental particles, remember that. Is constructed from combinations of some of these 12 particles and no other. So all matter in the universe is constructed from combinations of some of these 12 particles and no other. Each of the 12 particles listed in tables A and B, okay, so you can see tables A and B, each of the 12 particles listed in tables A and B also has an antiparticle. The antiparticles have the same mass, but all the other properties are opposite to those of the normal matter particle. Now again, this was under the definitions also, right over here. Same sentence is there. To write the symbol for an antiparticle, it is the same as the normal particle with a bar above the symbol. See, if you go through these notes here, you can see that I have oh, I can zoom it this way. Okay, that's better. Okay, you can see that I have shown that in this table. See, so remember, if it's neutrino, or if it's a neutrino, and if it's the antiparticle of that neutrino, we use a bar on top like this. So you would have seen this in the equations for beta minus and beta plus decay. See here, see, this is the neutrino, so we use a bar on top. Antineutrino, sorry, electron antineutrino. So we use, and we can also use a small letter E here to indicate that it is the electron antineutrino, to be very specific. Because if you look at the neutrinos, you have tau neutrino, muon neutrino, and the electron neutrino. Okay. To write the symbol for an antiparticle, it is the same as the normal particle with a bar above the symbol. For example, the charge on an anti-down quark is plus 1 over 3. Now remember the down quark, I told you an easy way to remember the charge of those quarks. Okay, so let's go back here. Now remember, what is that? If it's down, bottom, or strange quark, the charge is minus 1 over 3. Now what do we have here? We have anti-down. Can you see? Anti-down quark. So that means it's plus 1 over 3, because only thing same for the antiparticle is the mass. Everything else is the opposite. It's not different, it's the opposite. So again over here you can see, for each particle that there exists an antiparticle which has the same mass, but all the other properties are opposite. We don't use the word different, we use the word opposite to those of the normal matter particle. So over here, when we say anti-down quark we know has charge minus 1 over 3. So since it's anti-down quark anti-down quark, the charge is plus 1 over 3. For example, the charge on an anti-down quark is plus 1 over 3, and the symbol is D with the bar on top. Now remember, the symbol D, either capital or simple, was used, we use better to use simple. Okay, simple letters for all of them. We use for down quark, we use the letter D, and if you want to write the anti-down quark, we use the D with a bar on top, this one. Okay, and if you look at the notes again over here, what I wrote down, you can see here, mesons. Meson is made up of a quark and an antiquark. So hadrons are classified to baryons and mesons, and mesons are always made up of a quark and an antiquark. For example, if we look at the pi plus meson, it is made up of the up quark and the anti-down quark. Okay, now you can even figure out what the charge of this meson is. Okay, so up quark has charge plus 2 over 3, down quark has charge minus 1 over 3, and if it's anti-down quark, it will have charge plus 1 over 3. So this has plus 2 over 3, Okay, this has plus 1 over 3. So when you add the two together, it's plus 3 over 3, which means plus 1 charge. Okay, so you see plus pi plus meson. Similarly, you can also calculate the charge of this. Now, phi meson. Since it's a meson, it will have a quark and an antiquark. Now remember strange quark. I told you easy way to remember. Okay, strange means negative, right? Then negative 1 over 3. And this is anti-strange quark. So the charge will be plus 1 over 3. When you add these two together, it's 0. So this has 0 charge. In some questions, you will have to calculate the charge like this. Okay, of the particle. There are some questions like that. This is very important. Okay. Okay, then let's go back to what we were discussing. In a few cases, the antiparticle notation treats it as a different particle in its own right, and the bar may not be used. So you can see that over here when it came to the mesons. Okay, over here you can see electron, positron, muon, then the antiparticle of muon. Here we don't use a bar. We instead use the plus and minus signs. Okay, so let's see. In a few cases, the antiparticle notation treats it as a different particle in its own right, and the bar may not be used. The positron anti-electron, that is the beta plus particle, does not use a bar but is written as E plus. See, positron, also called the beta plus particle or the anti-electron. So 3 names to mean the same thing. Positron, anti-electron, beta plus particle. For this we use the E plus or beta symbol and then the plus. Beta minus is electron, beta plus is positron. So in the notes also it's here, see, this is the electron, this is the antiparticle of the electron, which is positron or anti-electron or beta plus particle. Then this is the beta minus particle or electron. Okay, all right, so that is the end of that. Now make sure you answer all these questions and check the answers in the answer script. We'll go through this a little bit for additional information. The Higgs boson, one of the aims of CERN, Large Hadron Collider. You can see this in Switzerland. So for more details you can go through this. It's also in the previous lesson in chapter 8.2. The CERN Large Hadron Collider. You can also visit this place. If you're going to Europe, you can book a tour and take a tour with some explanation about this place. A lot of particle physicists are here. One of the aims of CERN Large Hadron Collider LHC experiment was that it could discover the Higgs boson. This was theoretically suggested independently by both Peter Higgs and the team of Francois Englert and Robert Brouout in 1964. Itself very massive, the Higgs particle is the means by which particles get mass. Remember that one of the key points about mass is that it gives objects inertia, the reluctance to change velocity. That is what we mean by inertia. Thus, an electron suffers less of this effect from the Higgs field than a proton, and so it has less mass. The Higgs mechanism, how this field imparts mass, is not easy to describe in everyday terms. On 4th July 2012, 2 LHC experiment teams, Atlas and CMS, jointly announced that they had discovered a particle which matched the previous interactions of the Higgs boson, and the mass of this new particle was approximately 125 giga-electron volts per c squared. Whilst the LHC scientists were reluctant to confirm it as the Higgs boson at the time, the new particle discovery was good enough for Higgs and Englert to be jointly awarded the 2013 Nobel Prize in Physics. Brought had unfortunately died a year before the experimental discovery had confirmed. So for more information you can Google this. So what basically happens is that people could predict that this particle is there, and then scientifically they later find it out, something like that. Even I think they mentioned that about these other particles also, where they could predict, based on the calculations, they could predict that this particle exists, and afterwards they find out that it actually exists. They find it out, and they find out that particle. Okay, and here also I think they mentioned that, see, the symmetry of the standard model indicated to scientists that there were other particles that had never been observed which could exist, for example the bottom and top quark. Experiments were carried out to find these, and the accelerated experiments at Fermilab discovered, see, bottom quark in 1977 and top quark in 1995. Now this is like additional information, you can know them. Okay, so make sure you answer all these questions and check the answers in the answer script. Go through the important points and go through the notes also. These definitions are important. Next we will see particles and forces.